president of Incab America. And today, the webinar is entitled ACES CATS, but we're really going to be talking about ADSS sag and tension calculation in general. And you'll see that as we go. So to begin with, this is a RCEP compliant presentation, so the Registered Continuing Education Program. So if you would like to get continuing education credits, you can. At the end, I'll talk more about that, what you have to do. Okay. Oh, and by the way, this does not mean that they endorse, agree with, approve, or any other such thing with the content. It just means that we've met their standards for the presentation. The purpose statement rather, is that we're going to talk about how to obtain the sag and tension data that you need for your ADSS project. We're going to explain and illustrate the 3 methods of doing that, using tabulated data from suppliers, using ACES CATS, and I'll talk about that later, and also using PLS CAD. I will also mention in passing that SAG 10 from Southwire is another way of doing it. In the interest of time, I just chose to talk about PLS CAD. Then we're going to learn that the previous part is all wrong, but why it's nevertheless helpful. And then I'll tell you what you should replace it with. And along the way, we're going to talk about some important cable parameters such as maximum rated design tension and zero fiber strain margin. After this class, the learning objectives, you'll be able to get the SAG information that you need. You're going to understand why maximum rated design tension and zero fiber strain margin, what they are and why they are important and how you should be using them. You're going to understand how ADSS sag and tension data is done and understand the assumptions in that, and you'll understand as part of that what the difference is between a mechanically independent and a mechanically coupled span. And then you'll know when it's more appropriate to apply the ruling span concept and to use a program such as PLS CAD or Southwire SAG 10 to generate your sag and tension data for your cable. So webinar rules. So we've already done our introduction and sound check. Presentation may go a little bit over 45 minutes, and I beg your indulgence if it does. We'll have chat for questions at the end. The questions should be about the issue at hand, not questions about ongoing business. And let's get started. So I want to start off with 3 observations about ADSS sag and tension. Observation number 1 is some people think that ice doesn't accumulate on ADSS. So anybody who tells you that, you can get a copy of this slide and show them this picture. And what you actually see here, incidentally, is this ADSS cable obviously has ice accumulation on it. And there's another cable close by that doesn't. So that's of interest. But on the one that does, it only takes one cable to show that that is totally a myth. And what's also of interest here is notice how large the vertical sag is. And because ADSS is relatively stretchy, it means that ice loading can be increase sag significantly, more so than, say, a metal cable. And therefore, you could exceed ground clearance, and therefore you need to check that. Observation number 2 is, again, ADSS is light and elastic. And because of that, horizontal blowout during wind conditions can be significant. And again, it means it must be checked. And again, because it's elastic, strength is needed to control fiber strain. Fiber strain can lead to optical problems, including failure over time. And of course, this prompts the question, what exactly is fiber strain and why is it important? So let's take a little digression and talk about that. Fiber strain is quite simply tension on the fiber itself. Now, optical fiber is very strong, but it's glass, and that makes it relatively brittle. And as a consequence of that, keeping tension away from the fiber is a good idea. As I say here, no strain, no problems. If you keep tension away from the fiber, then you definitely won't have optical problems. So you are enhancing reliability. And because it's brittle, fiber is therefore vulnerable to cyclic loading. Things that are brittle don't like being loaded and unloaded and then loaded again and unloaded and so forth and so on. So again, if you keep the strain away from the fiber, you're enhancing your optical reliability. Throughout this presentation, we're going to talk about fiber strain margin, and that's the difference between the tension that's on the cable and the tension on the fiber. So the cable can have tension on it, but the fiber not. And the zero fiber strain margin is specifically the point at which the optical fibers begin to experience tension. As a general guideline, the higher the zero fiber strain margin, the better. Like any general guideline, there can be some exceptions, but as a general rule, this is really good. You want to keep tension off the fiber. So the higher your zero fiber strain margin, the better as a general rule. So now let's work on connecting these observations to today's topic. So in order to properly check your clearances, you've got to factor in your ice and wind loading. And in our industry, sort of a note here, the practice has been to have installation SAG be 1 to 1.5% of span. Installation, I will also call it in this presentation, everyday sag and tension. So no ice and no wind. So these have been the two most common values. More recently, I've seen 0.75% and 0.5%. In my opinion, these are risky because basically you're taking margin out of your cable performance, my opinion. So I like to stick to these two values. So you got to do the sag and tension calculations and factor in your ice and wind. And then you want to try to keep strain away from the fiber. So the best practice is to have zero fiber strain through maximum rated design tension. And I'll define that in a minute. And this is our design standard, but that's not always practical. Depends upon what you're otherwise trying to do mechanically and optically. But as best practice, this is as good as it can get. There are some alternatives that are acceptable, but you have to understand as the user that these do come with increased risk. So I absolutely insist that there should be no strain at the everyday condition. So nominal, unloaded, no ice, no wind condition. There never, ever should be fiber strain in a cable. It's okay to allow some fiber strain under the loaded conditions up to and including the maximum rated design tension. A good limit to use if you're going to allow some strain is 0.2%. This is a conservative limit that is derived from research that Corning did, but Corning did that research decades ago. And so one can argue that today's fiber is made better and more consistently. And so maybe I can up that 0.2%. Maybe I can allow 0.3% and be okay. And it's not an argument that I would necessarily want to do myself, but I can understand it's acceptable. But you do have to understand that you are increasing the risk of there being optical problems, because go back to what I said before, no strain means no problem, 100%. Anything else, you have a non-zero risk of there being some optical problems. Risky is to allow the strain to be 0.4%, and then greater than that, I think is just plain crazy. Now, here's like a little cable industry secret. All cable suppliers have a design policy on the fiber strain. It's not always disclosed to the users though. So that means that you can always ask them if you don't see the data on their cable data sheet, you can ask the manufacturer to confirm how much strain there is on the fiber at both maximum rated design tension, and ask them what the zero fiber strain margin is. So I promised to define maximum rated design tension, and that's just the term that the IEEE adopted in its fiber optic cable standards. More just as commonly in the industry is an older term, maximum rated cable load, or MRCL. We'll see that. You'll see that in a minute. Um, they mean exactly the same thing. They're just different terminology. I've decided to stick with the official IEEE terminology. What is it? It's the tension the cable should never, ever exceed under any loading condition. So whether it's the traditional NESC heavy, medium, light, or some hurricane force wind condition that you want to look at, you should never allow the cable tension to go above that point. It is absolutely not the same as the rated breaking strength of the cable. However, typically it's in the range of 50 to 65% of the rated breaking strength of the cable. So again, never ever exceed MRDT. You are risking optical problems if you do so. So the purpose of today's webinar is to talk about how you generate your sag and tension data, and it's done in 3 easy steps. First, you got to get your loading criteria. Second, you got to get the cable specifications, the data that you need. And then third, you get or generate the data. So we'll look at each step in detail. First up, review your loading criteria. So I broke this into a couple components. First, determine your base loading criteria. So here in the United States, it's NESC Rule 250B, the loading zones, heavy, medium, and light. If you're not in the United States, your country has probably got its own, and you know what they are. So um, now with OPGW, because I work with OPGW too, I often see customers have additional requirements beyond the base loading criteria. There's extreme ice, maybe want to look at an inch of ice or an inch and a half of ice. And there's concurrent wind and ice, which is generally a heavier ice load with a higher wind speed. These are in the NESC Rule 250C and D. Again, your country may have something different, or your state, if you're in the United States, there are some states that have specific criteria. So you can add these to your base loading criteria. And then your utility or your project may have specific tension limits or sag limits. And I say here a few, dude, just because I don't see additional criteria nearly as often with ADSS as I do with OPGW. But I just wanted to point out that, yeah, you can look at any and every criteria that you want to. So that's step 1, get your loading criteria. Oops. Step 2 is to get the data that you need. And it's basic cable data that should be on the manufacturer cable's data sheets. These include outside diameter, the unit weight, that maximum rated design tension. You got to get that from the manufacturer, the cable modulus, and we're going to talk about modulus a lot more later in the presentation, your linear expansion coefficient, and that strain limit. So what the zero fiber strain margin is, or what the long-term limit of the cable is. And we'll see some examples of this as we go. You're going to find that on the cable data sheet, as I mentioned, or you're going to have to ask the cable manufacturer. And so now what we're going to do is we're going to look at the data sheets of 4 manufacturers, just so you can see how this information is presented, because manufacturers tend to present it in slightly different ways. First up, no surprise, is Incab. What we do, you'll find here cable diameter on our data sheet, cable weight, maximum rated design tension, the zero fiber strain margin, and the modulus of elasticity. So here we're going to start hitting on that. Notice that there is an initial value, a final value, and a 10-year / creep value, and that these values are all different. We're going to talk about that more later. And we also have the coefficient of thermal expansion. So the 6 bits of information that I said you need, you've got it here. Next up is this company here. How do you pronounce this? Is it PRYSMIAN? Just kidding, PRYSMIAN. Very good company, by the way. They have their cable diameter, the cable weight, the maximum rated cable load. Remember, I told you that a lot of suppliers, it's an older term, but a lot of suppliers do use it. I still say that the official term should be MRDT. Going down, you'll find the initial modulus of elasticity. And look, they've got 3 values, but initial and final are the same. See this little note here. We'll talk about that in a minute. You've got your coefficient of linear expansion, and they've got this maximum tension at maximum span. Now we're going to see here on their data sheets where this comes into play later. For now, we just need to note that they have a long-term value. And for them, they're not explicitly saying that this is the fiber strain margin, but I do happen to know that it is. And I'll show you later when we look at how they present sag and tension data, how you can see that and know what that means. And then they have this short term. This value, 1575, is less than the maximum rated cable load, or MRDT, of 1581. And so what this means is that the maximum span that they presented their data at, that tension value was below the MRCL. We'll see it in a little bit, and it'll make more sense. Now, about those moduluses, initial equals final is not really the case. It's a simplification that's okay in the distributional world. And we'll talk about why they're simplifying it and a little bit later in the presentation. Okay. Next up is OFS. They have the cable diameter, the MAC cable weight. They have a tension at maximum span for 1%. Remember, I talked about 1% or 1.5% installation sag. So they've got this short-term maximum tension, which basically is maximum rated design tension. So they're using this terminology to mean maximum rated design tension, or if you prefer, MRCL. So 4,002 pounds. The cable modulus, and note that they only give 1 value. However, I can tell you that that is the initial value, and again, we'll explain why they're doing that later. You've got the linear expansion coefficient, and you have this long-term value. So they too are not giving direct information about the fiber strain margin. So they're just saying the long-term value is a maximum everyday value. Again, no ice, no wind. But that doesn't tell you anything about the fiber strain, or if that's the zero fiber strain margin point for this cable. So with this cable, you really don't know anything about where the strain begins on this particular cable. Next up is AFL, America Fujikura, and they have the cable diameter, the cable weight. You've got, again, they're using the MRCL terminology, and cable modulus, and notice initial 10-year final, and note that the values are all different. Coefficient of linear expansion, and then fiber strain margin, also not provided by AFL, and they're also not giving you an everyday or a long-term limit either. So for them, you got to ask. So We talked about getting your loading criteria. We talked about getting the data. Now we're ready to actually get the actual data that you need. So loading criteria, cable data, and now you get your sag and tension data. You got three sources. Traditionally in our industry, people have relied upon manufacturer-provided tables. Generally, you see them with standard NESC loading conditions, but a cable supplier can generate them for any other loading conditions. You just need to ask them. And then something we'll be showing here, Incab has this ACES, our Advanced Cable Engineering System, CATS, and you can generate your own. And this works for anybody's cable, as long as you've got the cable data that you need. And I'll show that later. And you can generate your own data using Powerline Systems PLS CAD, very popular design program, or Southwire SAG 10. Today, we're only going to talk about PLS CAD. So, like we did with the cable data, I want to show you how manufacturers provide sag and tension data. So, first up, no surprises, Incab. And basically, everybody does the same thing. There's header data and then the actual data. So for each supplier, we're going to look at two slides. So this is Incab's cable specifications and the key information like MRDT. Maximum every day for Incab means the zero fiber strain margin point. And you'll notice that for this cable, ideally, I said you would like your zero fiber strain margin and your maximum rated design tension point to be the same, but that's not always practical. And here's an example of that. So for this particular cable, there's a little bit of a difference between the two. You got your loading conditions confirmed. And then you've got the data. And the data is always presented for everyday condition, no ice, no wind. Sometimes it's called installation sag, and basically you've got span lengths, the amount of sag, and again, we talked about that sag is typically either 1% or 1.5% of the span length, and you see that confirmed with this data here, and then the tension at that amount of sag. Then you have the data for your loaded condition, and the sag, this is your total sag, and it's always broken out into horizontal sag and vertical sag in some format, and then the tension at that total sag. Here you also see the percent of a span. Horizontal sag is what you can use to check for blowout conditions, and then vertical sag allows you to check for clearance to other cables or ground. Next up is PRYSMIAN. Again, in the header, you see the cable specifications and the loading conditions confirmed. And I just want to point out on PRYSMIAN, what you'll see is fiber strain, and you'll see them say safe strain. And my intelligence sources have confirmed that safe strain means that the fiber strain is 0 at the everyday condition and less than 0.2%, we think, at MRDT. I'm pretty confident that this is correct. Safe strain. They also, you'll see 0 strain, and that means that the fiber strain is 0 at the everyday condition and 0 at MRDT. But you can always ask PRYSMIAN to confirm their values. And then here's their data. And again, you see the everyday condition, no ice, no wind, span lengths, the amount of sag. You see here they too have used 1.5%. You got the tension. And then under loaded conditions, you've got vertical sag, horizontal sag. You could use this to calculate the total sag. They're not presenting that for, oh, yeah, they're not presenting that. I'm not sure why. And they're giving you the cable angle. So note that the cable under the loaded conditions, which were, I forgot, medium, NESC medium, note that you got 45 degrees which is why you see actually the vertical and the horizontal sags are pretty close to identical because you're at a 45-degree angle. And then it's nice that they also show the ice only vertical sag. That's helpful. Okay. Next up, OFS. Again, basic cable data is here. You got your MRDT, this maximum every day. But again, that's not telling you anything about the strain that might be on the fiber. And then for them, I just wanted to point out that this shows what I was telling you. You can ask suppliers to give you data for any condition that you want. Here it says user defined. So that's not a traditional NESC loading district. That's something special. And then when you look at it, it's no ice and very high wind. 93 miles an hour or 100, almost 150 kilometers per hour. So that's basically hurricane force wind. And that should be interesting to see the results. So let's look at those results. Again, you've got your data for the everyday condition. Notice that they've used 1% of span for the everyday condition. Nothing wrong with that, it's just different. And then the data under loaded conditions. So you see the vertical sag and the horizontal sag, from which you could calculate the total amount of sag if you wanted, and you've got your tension information, and it stayed below that maximum tension that they gave. And then I just want to point out that because the wind speed is so high, look at the angle here. The cable is almost perpendicular to the ground at that wind speed. And even at a 500 feet, you've got nearly a 500-foot span, you've got nearly 20 feet of blowout. Wow. And then down here, maximum span of 1,276 feet, you got 56 feet of blowout. So I hope that underscores the point about why it's necessary to check for blowout for your for clearances. Next up is AFL. Again, you've got your cable specifications here with MRDT. But again, I point out that they don't give a maximum every day or a zero fiber strain margin. You have to ask. And then here's the data. They've opted to present the data a little bit different format than the others. This is just for a single span. What that's allowing them to do is that they can show multiple loading conditions at one time. They're not really showing that here, but you can see that they have the capability. Here on this one line is that everyday condition. And then here under the NESC light conditions, you've got the data that you need there. And then I'll just comment that they show vector. That just means the total sag. So, okay. So option one, you can get data from manufacturers like what we've just seen from 4 major suppliers. Option number 2 is that you can use Incab's ACES CATs. You know, if you need data and you need it now, well, go to use ACES CATs and you can get it now. That makes it easy to do any kind of what if analysis. I submit that it is fast, easy, and fun, but I admit that perhaps I've been working with aerial cables too long. And as I've said before, you can use this for any supplier's cable. And the way that you do that is you go to Incab America, our website, you select the configurator and then select the ACES CATs. Just to point out, you can save and reuse data. You enter the cable data, and then you hit calculate. And how are we doing? We're not doing bad on time. So let's actually go and do that. Okay, so hopefully you see ACES CATS calculation of tension and sags. This is from our website. I've gone here and I've set up a project before. And, just to show you, I could change the cable data here and just round it off and say 0.5 is close enough. And, if I can mix and match units, you'll notice when I did the cable diameter, it calculated the metric, but I can do the opposite, mix and match. So I can put the weight here in metric units, basic data again, modulus that we've talked about, coefficient of thermal expansion, MRDT, whatever limits you're using for everyday conditions. You can set up your loading condition, or you can add something that you want to do on your own. Heck, what the heck? Let's make the wind a little bit higher. This K factor is a US NESC thing for those of you that are not from the United States. I can just zero it out. Put in the temperature, how much sag you want. Today, let's say 1.3%, just for fun, and then hit calculate, and you'll get the data. And you can switch back and forth from customary units to metric units, and you can download the data as a PDF file. Which you can then share with all your colleagues or your family and friends, post it on your refrigerator, do whatever you would like. So let's go back to the presentation. Okay. All right, and we already talked about this. You can change the units, you can download the data. Now, that was all great. I hope you agree. But unfortunately, there's bad news. All of what I've just presented is what the current industry practice is, but strictly speaking, it's not correct. There are two things that are not quite right. All of the cable suppliers are using only the initial value for the modulus. If you check their data, you will see that they have used the initial value for modulus. You saw that PRYSMIAN set the initial value and the final value the same. That's the same thing. You're basically using the initial value of modulus. And what that is implying is that ADSS is perfectly elastic and that there is no difference between the initial and the final modulus and no creep to boot. And in the real world, we know that's not the case. And in fact, you can also see that it's not the case that 3 out of the 4 manufacturers gave different modulus values for at least 2 of the 3. So we know that's not true. The second thing is, or the second assumption that's implied by the current practice is that it's treating spans individually as if each is double dead-ended. And that's only true if each span is strung and clipped individually. The way that you could do that is you would use the so-called moving reel installation method, which most cable suppliers don't recommend, by the way, with a trunnion type support clamp. And that gives mechanically independent spans. So what that means is this span from dead end to this support clamp, and by a support clamp, I mean these pictures here illustrate that type of clamp. The clamp is fixed. It can't move or articulate. So this clamp is basically as if you had a dead end here and a dead end here and here, and another dead end here and here, and then another dead end. So each span is mechanically independent, right? The supports are creating fixed points at each pole, and that's what gives you the independence. What's more commonly used to install ADSS is the controlled tension stringing method. So back here, you would have a bull wheel tensioner, and you pull the cable from this pole to this pole to this pole to this pole. This is your pole polar, and the cable then uh, can move to equalize tension throughout all of the spans. And then you would go back and clip it in. Cross multiple, okay. And then if you, in addition to using the controlled tension, if you're using suspension clamps, then, and what I mean by that is clamps like this, these clamps can articulate or swing just a little bit, and it only takes a little bit to alleviate a tension unbalance from one side of the pole to the other side of the pole. And so that gives you a mechanically coupled system of spans. So the controlled tension and suspension clamps give you mechanically coupled spans, and therefore the ruling span concept is what governs the sag and tension. The tension equalizes across all of those spans, but the sag tends to be greatest in the longer span. So this ruling span is effectively a weighted average, and we'll give the exact formula in just a moment. Now, this then begs the question, well, what if I use the controlled tension stringing method, but I use the trunnion type support clamps? Well, you get something in between. So basically, I've created a continuum here between, you might say, fully mechanically independent spans and fully mechanically coupled spans, and maybe a couple of intermediate conditions that exist. But these two stake out the extreme, and that's enough for us to look at it and understand what this means. So you could be asking, does this mean that everything to this point was just a waste? And of course, the answer is no. It just means that you need to understand the limitations of this methodology that we've used. For short to medium spans in a distribution environment, the theoretical error is acceptable. That's my opinion, obviously. But I think it's a good opinion. Why? Because from experience, we know that there's not problems cropping up all over the United States or all over the world with cables clashing into each other or hitting the ground or anything like that. So in the real world, we're not seeing problems that could be directly attributed to the error in this methodology. And there's not just good luck behind that. The reason for that is that for ADSS, the change in sag and tension between the installation, or which is under the initial modulus, and the final, whether it's final or final plus creep or both, that change is much lower than that for a metal cable. So I estimate it about half. You can live with the error. And then in addition, in a distribution environment, let's face it, I think it's not, I think I'm not betraying any confidence or exposing some dark secret when I say that in the real world, distribution crews don't always follow exactly proper procedures. When it comes to sagging the cable, sagging of cables, even the metal cables, is often more done by, hey, that looks about right, than actually, making sure it's exactly per the stringing charts that they're using. I apologize if anybody who works in distribution is offended by that. But anyway, so this real world factor alone washes out any theoretical error. Again, this is my opinion. So I basically land on this is a simplified solution, and it works. It's I hate to characterize it this way, but it's good enough. Is it always good enough? Well, maybe not. And so in turn, this leads to then two questions. When would this so-called simplified solution be okay? And when it's not okay, what do I use instead? So when is it okay? Well, short and medium spans in a distribution environment. Okay, but what's a short and a medium span? Uh, Roughly, I'd say anything less than 5 to 600 feet, 150 to 200 meters, and understanding standard loading conditions. Now, we remember we saw OFS use hurricane force wind levels. Yeah, in that case, yeah, I might want to look at that in more detail. And so now I'm back to what should I use instead? Well, you should apply the ruling span concept, and you should be using uh, not just manufacturers' tables or the ACES CATs, but you should be using Powerline Systems PLS CAD or Southwire SAG 10. And you'll recall we said there are three sources of the actual SAG data: the tabulated data from manufacturers using ACES CATs, or PLS CAD, or SAG 10. And so if you're not under these conditions, then I think you should be using the ruling span concept and one of those programs. And I'm sure there are others around the world. So what is the ruling span concept? Well, here's the formula. Let's first talk about what it means. It's the square root of the sum of the spans cubed. So sum of the spans cubed, what that means, span 1 cubed plus span 2 cubed plus span 3 cubed, and so on, divided by the sum of the spans. Sum of the spans, span 1 plus span 2 plus span 3 plus so on. And that gets you your ruling span. It's effectively a weighted average leaning towards the longer spans. This cubed here is what's doing that. Today, using Excel, if you got a list of spans for your project, it is very easy to put a column over here and cube all of the spans, and a column over here, and then sum them up at the bottom, and then do the division and take the square root. Easy peasy to calculate the ruling span today. And PLS CAD can do it for you. I'm not sure if SAG 10 can do it for you or not. So here's an example. I got 4 spans across 5 poles. Here are the span lengths. Here's the math. In feet, you end up with 220.4 feet. And note that that's closer to this span than it is to the others. Right? It's longer than each of the others. In meters, you end up with 67.2 meters. And just for comparison, the average span 218.25 feet, or 66.5 meters. So the ruling span is a little bit longer than the average. That's why I called it kind of a weighted average towards the longer spans. Okay. Now, back to PLS CAD. With PLS CAD, you have to have a wire file. And it's good to know how to do what I'm about to show you, but it's a lot easier to just get a wire file from a cable manufacturer. You can also find a library of wire files by cable manufacturer at their PLS CAD's website. There's not as many ADSS cables as perhaps we would like. Maybe that's something I should be working on now that I think about it. But editing wire files for ADSS is not very straightforward. So I'm only going to talk about it very quickly. It's just a lot easier to get one from the cable manufacturer. But to show you what it looks like, you basically should start with an existing one, a donor file as I call it, and then you edit the data. So here, cable designation, more cable designation, who the cable supplier is, and basic cable data, you'll see, cross-sectional area, the diameter, the weight, rate of tensile strength. But here's where it starts to fall apart in terms of it's just weird. The program requires these 2 lines. I have no idea what they mean. And instead of the typical stress strain coefficients that transmission engineers and other aerial cable engineers are used to seeing with metal cables, instead you get this strange thing where it's a 0 and then it's the initial modulus, but it's in odd units, and then 0, 0, 0, and then the second line, the 10-year modulus, again, in strange units, and 0, 0, 0, and then the final modulus goes here, thermal coefficient, and then more stuff that's just required by the program, have no idea what it means, and then a bunch of other stuff that you shouldn't touch. And I put this, it reminded me of those medieval maps of the world where at the edge of the known area, beyond that, they would write, "Here be dragons." So, it's don't go there because we don't know it's there. And that's the situation here. There's just a bunch of stuff, no idea what it means. You just don't touch it, basically. So uh, to edit a wire file, you have to use Notepad. Well, you don't have to, but constantly over my career, I've gotten complaints from people. I send them a wire file and I tried to open it and it won't open. Yeah, it's a text file. Makes it a little bit odd. So if you use Notepad, you can open it and edit it. Then what you would do after you edit it is save the wire file. You load the wire file into PLS-CAD, complete your problem file, and then the program will crunch the numbers for you. And then with PLS-CAD and Southwire SAG-10, one thing I need to make you aware of is remember MRDT, and remember how critical I said it is. And remember that zero fiber strain margin or fiber strain margin is darn important too. You have to manually check in both PLS-CAD and SAG-10 to make sure that the tension doesn't go over that. Again, because if it does, you risk optical problems or avoided warranty, neither of which is good. And I just want to emphasize again, MRDT is a tension that you should never exceed on your cable. Really important. And you should also double check the fiber strain value as well. And just pointing out again, you can go use ACES. There are other components out there. The ACES CATS is the newest for doing these sag and tension calculations for ADSS, but you'll find other stuff that's helpful there. And I invite you to check it out. And that completes the formal part of our presentation. And I will now open the floor to questions. Figure out how to stop sharing my computer screen. You can use chat, raise a hand. Got any questions? Wow, quiet bunch today.
Hey, Mike.
Hey, Joe.
Got one question, and that is, what about the ADSS with the track resistant sheath? Will that be a different weight than the non-track resistant sheath? And would that be included in?
In general, any weight difference would be on the order of trivial. So I would still apply the guidelines that I gave here, that if you're using track resistant cable in a distribution environment, and of course by its nature, you're generally not. But we have a couple customers that they buy track resistant cable and they use it everywhere. And so I would use the method that I mentioned to you. I would, if you're working in a distribution environment, I'm okay with my so-called simplified method. And but if I was working in a transmission environment, I would use the ruling span concept. And I don't know what to call it exactly. Traditional cable analysis.
That's great. I just I didn't realize that the difference in weight might be insignificant.
Yeah, well, and between a non-tracking cable, the exact same cable design, a non-tracking cable and a tracking cable, the weight would be insignificant. But of course, in general, when people are using track resistant cables, they're using them for a transmission environment, and so they're stronger, and there's more material there, so therefore they do weigh more.
Right. Thanks.
You know, and also with the track resistant cable, like you're nearly, I mean, I don't know the exact number, but my guess would be 99% or more are double jacket design. So again, bigger, a little bit heavier. Whereas in distribution environments, customers, you know, money is everything, and so we'll go with single jacket designs, much smaller, much lighter. But you know, but literally for one utility in your general area of the country, uh, they adopted the use the track resistant everywhere, but we also have a non-tracking version of the cable because I forget why, but that came about. And so the two cables, I'd have to pull up the specs to verify this, but I'm sure that the weight is no different.
Okay, thanks.
Yeah, you're welcome. Let's see, other questions? Let's see here. I see in the chat. Oh, I did forget something. Okay. But here's what I forgot is this. So if you want to get credit for this, you'll get an email after this, after we close out today. And the email is going to ask you for some feedback, and please give us feedback. You know, I don't mind if people tell me that I suck or that I got this wrong or whatever. You know, we value the feedback and take it to heart. So please feel free to be very candid in your feedback. But you can give us feedback, and you can include ideas for other topics you'd like for me to cover or for somebody on my team to cover. If I'm not the most appropriate person, we can get some better talent to cover things. So give us, you know, things that are of interest to you that you'd like to hear about, and we'll work on it. But also in there will be a link. So a couple links actually. One link, you can find a recorded version of the webinar. So you can refer to it later. Again, send it to family, friend, or colleagues. You know, if it's 2 o'clock and you can't sleep and you need something to help put you to sleep, you can bring it back. But then finally in there is a link that's going to take you to a quiz. There's 10 questions. You answer the questions, and you have to get 70%, and you pass, and then we give you the credits, and we credit you through the RCEP organization. And I will tell you that the questions for this webinar will require that you have to go to ACES and actually use it. Not all of the questions, but 3 questions will require that you actually use the program, and not just for our cable even. So try it out. Okay, back to questions. Metallic Tufik. Oh, another fine name.
I don't know if it is easier to ask.
Oh, it doesn't matter. Metal cables are using family of files. Using.
Depending on, yes.
Same based on strength member of aramid. I don't know the answer to that question. The ADSS has a lot more variability to it. Inner jacket, yes or no? How thick is it? And aramid is not always aramid. So there are different grades of aramid. And I'm thinking though that the variation of ADSS design is such that it may not lend itself well to the same kind of method that's been used with OPGW and metal cables, where you look at the ratio of aluminum to steel. It's an interesting thought, and I think the grades of ADSS are what really wrecks that as a possibility, because you know, when you're looking at steel and aluminum, you know, they're basically treated as steel and aluminum, and that's it. We don't think about the difference between a high strength steel versus a standard strength steel versus something else. You know, all of the steel is under one category per the ASTM, but with Aramid, the different grades and what you use totally depends upon what you're trying to do. So I don't think that's possible. I think you have to rely upon the cable manufacturer to grind the math and say, okay, here's what the modulus values are. And then let's see, I had a comment here from Dimitri. With ACES CATs, you don't have to wait for new calculations from a supplier if your requirements are changed. Yeah, exactly. That was my comment about you can do what if analysis, and you can, you know, while away the whole day just doing what if analysis and looking at different conditions. So any other questions or comments? Okay, going once, going twice. Okay, well, I appreciate everybody's time and attention, and some good questions there at the end. And yeah, thanks for participating, and have a great rest of your day. Take care. Bye-bye.
Thank you.
You're welcome.
Thank you.
You're very welcome.
Thank you much, Mike. This is Monty.
Hey, Monty. Good to see
Yeah.
you on too.
I'm still
Hey,
around.
Alexa, you can go ahead and stop the recording.
Yeah.
But Monty,